We're going to start with a problem that matches the first free body diagram that we did earlier. So we're going to put some numbers to this and actually do some calculations. So the idea with this question is a car is driving in a circle. If a car is going in a straight line and you were to imagine the tires, they would sort of be straight, right? But as soon as it's going in a circle, the tires sort of turn. This might be exaggerated, but the tires turn. There's a force of friction between the tires and the road that allows the tires to grip the road. And that creates a force which actually causes it to turn. Remember, when we're talking about centripetal or circular motion, we can see that the velocity of the object is tangent to the curve, and the force is actually directed towards the center of the curve. And in doing that, you end up getting an acceleration, a centripetal acceleration, that's directed towards the center of the circle. Remember, we're not actually moving towards the center of the circle. You're accelerating towards the center. What that means is your velocity is changing towards the center a little bit each time as the car drives around the road. So as the car progresses around the road, you can see the direction of the velocity vector changes, and it's always tangent to the curve. So, all right, so here are the numbers. So the question is asking in part A, what centripetal force must be supplied by friction in order to keep the car from skidding? Well, we know that the centripetal force is not an actual force, it's the sum of the forces. And the sum of the forces is equal to mv squared over r. We used to say ma, but since AC equals v squared over r, that's kind of where we get this equation from. This is the one we're going to use each time we try one of these problems. So in this case, there's really only one force along the direction of the motion. So one of your questions might be, why don't we deal with the engine force, the force that makes the car move forward? And we're kind of assuming that whatever force is moving the car forward, like maybe you want to say the force of the engine, is being exactly matched by whatever backward force there might be, like air resistance. So those two forces cancel out. And so the only force that's changing the motion of the car is directed towards the center. That's because we're assuming this constant velocity of 20 meters per second. So we're not going to worry about the sort of tangential forces. We're only going to deal with the circular forces. It's a way of simplifying the problem. Obviously, it's possible this car could be speeding up as it's going around the bend, but that's a sort of a different problem. So we're taking out that layer of complication. All right, so and then in our case, we have the situation where the centripetal force, Fc, which is the sum of, so the sum of the forces is friction, and that's equal to mv squared over r. So the question is asking what centripetal force must be supplied by friction. So that's kind of what we're dealing with here. So what we're saying is if this car is going to make it around the curve, it has a mass of 1,000 kilograms. It's moving at a speed of 20, and we're going to square that because of the equation. And it's going around a turn that's 80 meters in diameter. So when we do that calculation, we end up with 5,000 newtons. So what we're saying here is that there must be 5,000 newtons of force supplied by friction. Friction. All right, so that's the only way this car will make this turn. Part B says, what minimum coefficient of friction between the wheels and the road is necessary for this turn to happen? So in this case, for part B, we know that the force of friction has to equal 5,000 newtons. So what we're going to say is, but friction is just mu Fn, and that has to be 5,000. So mu Fn, we're going to calculate mu, so we're going to say this is equal to 5,000 divided by, now, since this is a level turn, we know that Fn is equal to Fg. And this, we can't draw it on this diagram because of the way it is, but we know that Fn is equal to Fg. So we're going to call this 1,000 divided by 9.8. And so when we do that, our mu works out to 0.51. 0.51. And so those are the answers to these two questions. Now, what that means is if you don't have 0.51, a coefficient of 0.51, it can't make the turn. So the next part of the question says, what happens if there is an icy patch and the coefficient decreases? So you can imagine a situation where, you know, there's a patch of ice on the ground. So this is the icy patch. And let's say mu is only equal to 0.1. It's greatly reduced. So if mu is equal to 0.1, then the force of friction, I'll do it in the icy color, then the force of friction, so on icy patch, Ff equals mu Fn, which equals 0.1 times 9.8 times 1,000. So in this case, it's 980 newtons. So on that icy patch, only 980 newtons of force is supplied by friction. So what we're saying is this car cannot make a turn at that rate, because what it needs, if you look at this equation here, what it needs is 5,000 newtons. So the only way you can change it is by, so this is the force you have. So what you can say is, well, let's set this equal to mv squared over r. What are the things that we can change? You can change the speed. You can reduce the speed, right? And that will decrease the force needed from this 5,000 number, or you can increase the radius of turn, the radius. And that's what happens when a car skids. It spins out. So instead of following the road, this car might hit that icy patch and spin off. And what it's actually doing is just increasing the radius of its turn, which minimizes the amount of friction it needs so that it gets it to work, to make it around that turn.